I'm him. This is PCBC. If you've ever done any RF related design, you must have seen this number. 50 ohms. Wi-Fi is 50 ohms, and well, antennas are also 50 ohms. RF test instruments. Even coaxial cables, well, they're all 50 ohms. So here's the question. Why is it specifically 50 ohms? Why not 20 ohms? Why not 100 ohms, or even a number that looks more rounded? Today, let's take 5 minutes to thoroughly explain this question. First of all, impedance mismatch causes reflections. To understand 50 ohms, we first need to understand a concept. What is impedance matching? A lot of people, when they hear the word impedance, immediately think of complicated formulas, but actually you can just imagine it as a water pipe. Imagine you are holding a powerful high-pressure water hose. If the entire length of the hose is the same thickness throughout, the water will flow forward very smoothly. But what if the opening suddenly narrows or constricts at the very front? What do you think will happen? That is right. Part of the water will actually be pushed back. In the world of radio frequency, this phenomenon is called reflection. For high-frequency signals, PCB traces are not just simple wires. It's more like a highway. Signals travel inside it at nearly the speed of light. If up ahead, everything is 50 ohms, and the impedance at the back is also matched, then the signal will flow smoothly all the way through. But if the front is 50 ohms, then the back is 100 ohms, the signal will sense that, hey, the environment ahead has changed. As a result, part of the energy continues to propagate forward, while the other part turns back and returns. This is what we call reflection. The consequences of reflection include power loss, shorter communication distance, a worse standing wave ratio, and reduced antenna efficiency. So for RF systems, impedance matching isn't just a bonus, it's a basic requirement. Have you ever wondered, so why do we specifically settle on 50 ohms? Since impedance is so important, why did we specifically settle on the number 50 ohms? The answer actually comes from an engineering compromise. Early RF engineers discovered that if you want to transmit the maximum power, then the optimal impedance is around 30 ohms, right here at this point. A transmission line of the same size can deliver more energy. But if you want the transmission line to withstand higher voltages and prevent breakdown, the optimal impedance is close to 77 ohms, which is at this point. In other words, 30 ohms excels at delivering power, while 70 ohms excels at withstanding voltage. Each is outstanding in its own way, but it's impossible to have both at the same time. So engineers made a classic decision. They chose a compromise value, which is 50 ohms. It offers decent power transmission capability. It also has good voltage resistance, making its overall performance the best. This is the real reason why 50 ohms was chosen. It's not the theoretically optimal solution, but rather the best balance point in practical engineering. In fact, 50 ohms wasn't just a number someone came up with out of thin air. During the rapid development of radio technology in the last century, the renowned Bell Labs conducted a large number of experiments on transmission lines and impedance matching. Engineers tested the overall performance under different impedances. They considered power, voltage resistance, and actual manufacturing conditions, and ultimately found that 50 ohms could meet the vast majority of system requirements in RF scenarios. Subsequently, this standard was widely adopted in military communications and broadcasting fields, and later on, Wi-Fi, Bluetooth, GPS, satellite communications, and radar. Even your mobile phone continues to use this standard. After nearly a century of validation, 50 ohms has become the common language of the entire RF industry. Finally, there's a very commonly misunderstood issue. Many newcomers, when they first hear about impedance matching, think it just means soldering a 50 ohm resistor onto the PCB. The answer is that's absolutely not what it means here. 50 ohms is not a resistor, it refers to characteristic impedance. It is determined by the structure of the PCB, mainly the trace width, the thickness of the dielectric layer, the thickness of the copper foil, and the dielectric constant of the PCB material itself. These parameters together determine the final impedance of the transmission line. So when a PCB manufacturer tells you that this is a 50 ohm impedance controlled trace, what it really means is that the entire transmission path has been designed to be 50 ohms so that signals can be transmitted stably, reflections are avoided, and system performance is ensured. All right, that's all for today's content. Thank you all for watching.